Good morning students, welcome to Bindu Dhadwal chemistry lessons. In today's lecture, we will understand the concept of redox reactions in terms of oxidation number. But before we understand oxidation number, let us recap the redox reaction in terms of electron transfer reactions. According to classical concept, sodium is getting oxidized because oxygen or an electronegative element is being added to it. There is loss of electrons also. Sodium lose one electron to form sodium ion. Similarly, chlorine from zero oxidation state will gain one electron to form chloride ion. So loss of electrons is called oxidation and gain of electrons is called reduction. So chlorine is being reduced and sodium is being oxidized. Similarly, when sodium and oxygen combine, they form sodium oxide. Sodium is oxidized and oxygen is reduced. Then when it combines with sulfur, sodium gets oxidized to +1 oxidation state -2. So there is gain of electrons. So in other words, loss of electrons is called oxidation and gain of electrons is called reduction. So the reaction in which both oxidation and reduction are taking place is called redox reaction. Now this is for an ionic compound where we know that the transfer of charge is complete. That is, sodium acquires complete positive oxidation charge and sulfur will attain complete negative charge -2. But if we take the example of a covalent compound, water, hydrogen will move to +1 oxidation state, but transfer of charge is not complete. In water, there is oxygen is more electronegative than hydrogen, so a partial negative charge is attained by oxygen and partial positive charge is attained by hydrogen. So this concept means that transfer of electrons from a less electronegative atom to a more electronegative atom. So we rewrite these equations. Hydrogen from 0 changes to hydrogen to +1 state. Oxygen from 0 changes to oxygen with -2 state. So there is a loss of electrons from 0 to +1. This is oxidation. There is gain of electrons from 0 to -2. This is reduction. Although we are showing here that there is a gain of electron, but we know that in covalent compounds this is only partial transfer. There is only electron shift, and these assumptions are only for bookkeeping purposes. In reality, the transfer of charge is only partial. So accordingly, we can define oxidation number. It is the oxidation state of an element in a compound which is determined or ascertained according to a set of rules formulated on the basis that electron pair belongs entirely to the more electronegative element. So once again, it is the rules decide that the set of electrons belong to more electronegative atom, even though in reality the transfer is only partial. Let us now discuss how we make use of the rules for calculation of oxidation number. So we'll study the rules one by one. Rule number 1. In elements in the free or in the uncombined state, each atom bears an oxidation number of 0. For example, hydrogen in its elemental state exists in the form of H2. So the oxidation state or oxidation number of hydrogen when it is existing as H2 is 0. Oxygen exists as O2. oxidation number will be 0. Ozone, it exists as ozone, then also its oxidation number will be 0. In phosphorus, in the elemental state, it exists as P4, so its oxidation number will be 0. Similarly, for S8, it's 0. For sodium element, it's 0. For magnesium element, it is 0. And for aluminium element, it's again 0. Second rule, when the element is in the form of iron and it is composed of only one atom, then the oxidation number will be the same as the charge on the iron. For example, sodium ion exists as Na positive, so its oxidation number will be +1. Magnesium dipositive ion +2. Ferric ion +3. Chloride ion -1. Oxide ion -2 will be the oxidation number. In their compounds, all alkali metals have oxidation number of +1. So let's write down the alkali metals: lithium, sodium, potassium, rubidium, cesium, francium. So alkali metals, in all the alkali metals, the oxidation number will be +1. So potassium +1, rubidium +1, cesium +1, francium +1. So in their compounds, all alkali metals have oxidation number of +1. Similarly, in their compounds, all alkaline earth metals have an oxidation number of +2. So beta, mange, car, scooter, Bab, Roe, beryllium, magnesium, calcium, strontium, barium, radium all have an oxidation number of +2. All alkaline earth metals have an oxidation number of +2. And aluminium will have an oxidation number of +3 in all its compounds. So let's recap. In elements in the free and uncombined state, each atom bears an oxidation number of 0. For ions, the oxidation number will be same as the charge, and in their compounds, alkali metals will have oxidation number of +1, alkaline earth metals oxidation number of +2, and aluminium will have oxidation number of +3 in all its compounds. Rule number 3. The oxidation number of oxygen in most compounds is -2. So, oxidation number of oxygen will be -2. Oxidation of number of oxygen will be -2. But there are exceptions. In peroxides and superoxides, there is a change in oxidation number of oxygen. For in peroxides, where oxygen is combined with itself, the oxidation number will be -1. Similarly, in sodium peroxide, it will be -1. So in all compounds, it is -2, but in peroxides, it is -1. In superoxides also, because this is +1 always, this will be -half. 2 into half is 1, so +1 and -1. Similarly, in rubidium superoxide RbO2, it will be -half. Oxidation number will be -half. The exceptions are peroxides and superoxide, and then when oxygen is bonded to fluorine. In that case also, because fluorine is more electronegative than oxygen, fluorine will have a negative oxidation number, and of oxygen fluoride it is +2, and in case of dioxygen difluoride it is +1. The oxidation number of hydrogen is +1 except when it is bonded to metals in binary compounds. In normal compounds it is +1. For example, in HCl it is +1. But when it is bonded to a metal and the compound is of two elements only, hydrogen and the metal, then it shows an oxidation state of -1. In lithium hydride hydrogen will show -1, in sodium hydride -1, and in calcium hydride -1. So generally oxidation number of hydrogen is +1, but when it's bonded to metals in binary compounds, then it is -1. Then in all its compounds, fluorine has an oxidation number of -1. Other halogens, chlorine, bromine, iodine, also have an oxidation number of -1 when they occur as halides. For example, NaCl, sodium chloride, it's -1. NaBr, it's -1 for bromine. But when in combination with oxygen, chlorine, bromine, iodine, it can have positive oxidation state also. Similarly, in oxoacids and oxoanions, it can have positive oxidation number. So normally when halides, these halogen, chlorine, bromine, iodine will have -1 oxidation state. But when in oxoacids, it will be having plus positive oxidation states. For example, in hypochlorous acid, oxygen has -2, hydrogen is +1, so resulting chlorine has +1. Similarly, in oxochloride ion, it will be having -2 and plus, let it be x, -2 plus x is equal to -1. So x is equal to -1 plus 2, that is +1. So chlorine, oxidation number of chlorine in OCl negative is +1. So in all compounds, fluorine has -1 always. Other halogens have -1 when they occur as halides. But when they are combining with oxygen, for example in oxoacids and oxoanions, they can show positive oxidation state. Rule number 6. The algebraic sum of the oxidation number of all the atoms in a compound must be 0. For example, if the compound is Na2SO4, it's a neutral compound, so sodium will always have +1, oxygen will always have -, sulfur in this case has +6. So when we add all these up, the net result is 0. Let's check it out. 2 into +1 plus 6 into 1 atom plus 4 into -2. So this is 2 plus 6, 8. This is -8. 8 minus 8 is 0. So algebraic sum of oxidation number of all atoms in a compound must be 0 if the compound is neutral. If the compound is an ion, in a polyatomic ion, the algebraic sum of all oxidation numbers of the atoms of the ion must equal to charge on the ion. For example, carbonate is a polyatomic ion. It consists of 4 atoms, 1 of carbon, 3 of oxygen. The net sum of the algebraic sum of all the oxidation numbers will be the charge -2. So that means the charge on carbon plus the sum of charges on oxygen, the all will come out to be -2. So using these rules, we can find out the oxidation state of carbon. So if it is X, then X plus 3 into -2 is equal to -2. So X minus 6 is equal to -2. X is equal to -2 plus 6. X is equal to plus 4. So the oxidation number of carbon will be plus 4. So you can see that using these rules, we can find out the unknown oxidation number of element. We now know that metals will always have +1 plus positive oxidation state. Non-metals can have negative oxidation state as well as positive oxidation states, and the transition elements can display several positive oxidation states. If we move in a period, for example, in the third period, as we move for representative elements, which are group 1 and 2 and group 13 to 17. These elements will have their maximum oxidation state according to their group numbers. For group 1 and 2, the maximum oxidation state will be the same as their group number. That is, for first group, it will be, because group number is 1, or maximum oxidation, highest oxidation number or state will be +1. For second group elements, for example, for magnesium, it will be +2. For group 13, the maximum oxidation state can be calculated by subtracting 10 from group number. 13 minus 10 is 3. So maximum oxidation state will be 3. For example, in AlF3, aluminium shows +3 oxidation state. For silicon, it will be 14 minus 10, 4. For phosphorus pentaoxide, it will be 15 minus 10 plus 5. So this is +6 for SF6, and for chlorine, the maximum oxidation state can be +7 as in HClO4. So these are the examples of compounds in which the element belonging to these groups is showing the maximum or the highest oxidation state. A term that is often used interchangeably with the oxidation number is oxidation state. So in carbon dioxide, the oxidation state as well as oxidation number of carbon is +4. Similarly, the oxidation state as well as oxidation number of oxygen is -2. The oxidation number or state of a metal in a compound is sometimes presented according to notation given by German chemist Alfred Stock. It is popularly known as Stock notation. For example, in Aurous chloride, gold is in +1 oxidation state. So according to Alfred Stock, it can be written as Au. We write the oxidation state in Roman numbers in brackets or parentheses, and then we write the next element. So Au1 chloride is the Alfred Stock notation of writing Aurous chloride. And similarly, auric chloride has oxidation number of gold as 3, +3. So we write gold auric chloride as Au, then 3 in Roman numbers in parentheses, and then Cl3, Au3Cl3. Similarly, stannous chloride is written as Sn2 chloride because oxidation number of tin is 2 here, and stannic chloride is written as Sn4 chloride. This change in oxidation number implies change in the oxidation state, which in turn helps to identify whether the species is present in oxidized form or in reduced form. For example, mercurous chloride, mercury 1 chloride is reduced form of mercury 2 chloride because Hd2 positive will gain an electron to form Hg1 positive. So it will gain electron and get reduced. So Hg1 chloride is the reduced form of Hg2 chloride. Using Stock notation, represent the following compounds. So because according to the rules finding the oxidation number, we get the oxidation number of gold as 3. So according to Stock notation, we can write it as HAU3 chloride. Similarly, thallium oxide oxidation number will be +1. So we can write TL1O, TL2-1O. FeO oxidation state is +2. So we will write Fe2 oxide. Here it's +3. We will write Fe2-3O3. For copper, we will write CuI. This is -1, so this is +1. So oxidation number will be +1. So compound will be written as copper 1 iodide. Similarly, this has plus 2 oxidation number, it will be written as copper 2 oxide. Here it's plus 2, so it will be Mn2O. Here it's plus 4, so it will be written as Mn4O2. This is the alphabet stop notation of writing these compounds. We clearly show the oxidation state in parentheses in Roman numbers. Now to summarize, a species which is undergoing increase in oxidation number is called oxidation, which is undergoing decrease in oxidation number is called reduction. A substance which causes increase in oxidation number is called oxidizing agent. A reagent which lowers the oxidation number of an element is called reducing agent, and the reactions which involve change in oxidation number of the interacting species is called redox reactions. That's all in today's video. Thank you. Have a nice day.